All right. So this is October, November 2017, Unit 1 paper. All right. So which of the following SI quant units is only used with a vector quantity? So which of these is only used for a vector quantity? Meters per second squared. This is a unit of acceleration, and acceleration is only a vector quantity. It's not a scalar. One is in, let's look at the marking scheme as well. Is D. Yep. Okay. Then question 2 says an athlete runs a race around half a circle or path radius 30 meter used inside the lane. All right, 30 meter is okay. This is the inside path, and this half a circle has been run. At the end of the race, what is the magnitude of the displacement of the athlete from the starting point? This was the starting point of the athlete, and this is the ending point. So displacement is actually the shortest possible directed distance. So this is going to be the displacement, which is actually the diameter of this circle, this inner circle. So it's 30 plus 30, which is 60 centimeters. Okay, so option D. And question 3 says a ball of mass 0.04 kg is dropped from a height of 1.5 meter. What is the kinetic energy of the ball just before it hits the ground? Okay, you've been given the height and it has been dropped from there. So the potential energy which was stored in the ball at that particular height would be converted entirely into the kinetic energy of the ball before hitting the ground. So just calculate the potential energy using the formula mgh, and that's the kinetic energy just before hitting the ground. It's going to be 0.04 into 1.5 into 9.81. The answer to this would be your final answer. Okay, you could just calculate that. I'm not doing that. Question 4. An object is dropped from rest in vacuum. Which of the following is a correct graph of the velocity against displacement as per the motion of the object? Object is dropped from a certain height. Okay, and it's dropped in vacuum, so this means no air resistance is there. If no air resistance is there, that means acceleration is going to stay constant at 9.81. Now if the acceleration is constant, initially the velocity of the ball was 0 because it is dropped. Okay, dropped means it's dropped from rest, and rest means it's 0. So the graph has to start from 0. It's either going to be A, C, or D. And since the acceleration is constant, acceleration represents the gradient of velocity time graphs. So therefore, it's the gradient of the graph is going to stay constant. So it's option D. Okay. Then 5. As raindrops fall, they reach a terminal velocity. Which of the following properties has a negligible effect on the terminal velocity of the raindrop? Terminal velocity is the constant velocity which is reached when the upward resistive forces balance the downward weight of the object and net acceleration becomes 0. Now they want us to identify which of these is not gonna affect or has negligible effect on the terminal velocity. Density of the water itself, the water which was in here, the water in the raindrop, its density, will it have any effect? Well, we don't know. Let's see. Viscosity of the air. Viscosity of the air might add to the resistive force of the air or the drag force of the air. Viscosity of water, viscosity of water itself, or the volume of the raindrop. Okay, so volume of the raindrop will have its effect because the greater the volume, the greater the air resistance, and the greater the air resistance means that it will more quickly reach the terminal velocity, and the smaller the volume, then it would take more time for it to reach the terminal velocity. So the volume will affect the terminal velocity. Viscosity of the air. Okay, if the air is more viscous, sorry, the water, if the water is more viscous, then that means it will experience more air resistive force from the air. Okay, and if it is not viscous, then that means the water particles won't experience much resistive force. Think of it this way: if you've got air particles, the air water particles, since it's a liquid, the water molecules are going to be close to one another. Okay,
I got it.
and so if they are close to one another, they'll experience more force, more resistive force. That will also affect the terminal velocity. Viscosity of the air. If the air is more viscous, then of course the resistive force is also going to be high. So the only option left is density of the water. So let's see. Oh wait, A is not correct because weight. Oh wait, density can be linked with the weight as well, right? Density is mass upon volume. The greater the density, the greater the mass. The greater the mass means the greater the weight. So yeah, density will have its effect. The answer option which they have given us is viscosity of water. So that means this will have a lesser effect as compared to the density, because density, of course, it directly affects the weight, right? So that's why viscosity of water itself would have the least effect. Although this will also affect it, but like the negligible effect or the least effect would be due to the viscosity of water. This graph would have been correct if the axes were labeled with velocity and time, then it would have been a straight line through the origin. But since this is velocity against displacement, then what do you think would be the graph? Well, okay, think of it this way. You've got the velocity, this is the ball, and it is dropping. As soon as it drops downwards, it covers some displacement, right? And just before hitting the ground, the velocity of the ball will reach its maximum value. So as the displacement reaches the maximum value, the velocity will also reach a maximum value. Okay, so as displacement increases, the velocity will increase. But what about the gradient of this graph? Will that be a constant or not? Well, for that, you'll need to look at the gradient. This is change in V upon change in S. Change in V upon change in S, if you break it down into SI base units, is going to be meters per second divided by meters. Meters per second divided by meters means this is the S inverse. S inverse means 1 upon time. So the gradient over here is representing 1 upon time. So as time passes, will the value of 1 upon time increase or decrease? As time passes, is the time increasing or decreasing? Answer this, please. As time passes, will the time increase or decrease?
Increase.
So if the time increases, will this factor increase or decrease 1 upon t? If the denominator is increasing, then this entire factor has to decrease, right?
Yeah.
So that's why the gradient has to decrease as we go ahead. It's not gonna stay constant, okay? That's why option C is better answer than D. Actually, that's the only correct answer, not D. Okay, be very careful. This was a tricky question. If you had been careless like me on the axis, you would have gotten wrong as well, okay? And we've discussed 5 as well. So
Wait, can you explain it again?
yeah, this one, 5.
No, the graph one.
I said if you want to look at the gradient. Now you've determined that as displacement increases, the velocity will reach its maximum value. So it's either going to be A, C, or D. It cannot be B. All right. Then look at the gradient. Will the gradient stay constant? Will it keep on decreasing as time passes, or will it increase? So for that, you'll need to identify what the gradient will look like. The gradient is change in Y upon change in X, meaning change in V upon change in displacement. Velocity's unit is meters per second, and the displacement's unit is meter. So meters and meters will cancel out. What's the unit left? It's S inverse, right? Second inverse. Second inverse means it's a unit of 1 upon the time period, right? 1 upon time. This is the factor that you get. This is your gradient. Now, as time passes, as the ball falls, the ball will fall, the time will increase. And if the time will increase, the gradient has to decrease. So this means it's going to be a graph whose gradient, whose slope is decreasing, okay? It cannot be D because over here is constant. Or if you look at C, the gradient, it was initially max, and then as time passes, the gradient is decreasing. And over here, as time passes, the gradient is increasing. So again, it cannot be A. It has to decrease. It has to fall. That's why it's C. Clear?
Yeah.
And 5, do you want me to explain, re-explain question 5 too?
No.
All right, 6. Seashells are protective outer coverings, casings of some sea creatures. The shell is left behind when the creature dies, and the shell is moved around on the seabed by the tides and waves. Shells washed up on the beach are found to be as smooth as when the creature was alive. This is because the material from which the shell is made is, okay, why is it as smooth as it was alive? All right, this doesn't really look like, okay, yeah, it's gonna be strong, tough, stiff, or hard. Okay, so you've got protective covering
So it's going
casing.
to be hard.
It's gonna be hard.
Yeah, hard because hardness is the resistance of its surface, like resistance of the surface getting scratched.
Then why not stiff? Why not strong? Why not tough? Aren't they
Because
also
we're talking about its smoothness, that
smoothness?
is the surface.
Four forces act on the athlete.
The reaction force. Why is the reaction force acting to the left?
We'll see about that. It's not a reaction force, it's a resistance force.
Oh, sorry. It's the resistance. Oh, okay. Wait, never mind.
Yeah, this is resistance, this is the weight. And as the athlete goes forward, the force is going to be forward. And where will the normal reaction force be? Normal reaction force is opposite to the weight, right?
Then it's going to be
The weight, and listen, he's moving with constant
the
velocity.
bottom left. Is it the bottom left?
Let's see. Let's check it out. I haven't looked at them yet. Okay, he's moving with constant velocity. That means that all the net forces, meaning the force acting forward and backward, are equal. And the normal reaction force and the weight have to balance each other out. Okay, so now let's see. Which of the following diagrams correctly show the forces acting on this athlete? So the weight and the normal reaction force, the force and the resistive force. I think it should be B. You think it's C?
Wait, I didn't see the F1. Okay, wait. Can you scroll up?
Yeah, there's a force acting forward as well. Friction between the shoe and the ground force, F. That
Yeah.
friction,
See?
the friction which is acting backwards is
That
not
would be
actually acting backwards because the shoe is going back. So the friction would be acting forward, okay?
Wait, why?
Because the shoe, look at the foot of this person. The foot is going back. So friction always acts against motion. Friction has to act forward.
Oh, okay.
This is a tricky one. That's the answer. Okay, is B. Then 8. A bird flies with constant velocity 4 meters per second through air heading due south. Okay, it's heading south. This is south and the velocity is 4 meters per second. Due to the wind, the air is moving at 3 meters per second in the direction from east to west. This is your east, this is your west. So from east to west, there is a wind of 3 meters per second flowing. The magnitude of the resultant velocity of the bird is, all right, for the resultant velocity, just add them by head to tail method. So if this is our first vector, on the head of the first vector, add the tail of the second vector, the 4 meters per second, and find out the result.
So diagonally from.
Yeah. So this angle, okay, you actually just made a right angle triangle, and this is a 3, 4, 5 triangle. So this hypotenuse is this is of,
Pythagoras.
yeah, Pythagoras theorem. Then 9. A ski lift carries skiers along 450 meter slope with a which is inclined at 25 degrees to the horizontal, and it's a 450 meters slope. Okay. Now, it can be assumed that the motor has to lift an average additional mass of 80 kg for each skier using the ski lift. Okay, so for every skier, it has to lift how much? 80 kgs for every person. Then, which of the following expressions represents the work done against gravity when lifting an individual skier up the slope? So what's going to be the work done against gravity? Okay, for the work done against gravity, all you need to do is just find out the gravitational potential energy. And for the gravitational potential energy, you have to apply the formula mgh. M is 80 kg because we have to look at the individual, one person. G is known, and H, to calculate the H, you'll need to consider this right angle triangle. Okay, this is a triangle. And you know that the hypotenuse is 450 meters and this is 25 degrees. So if you take sine of 25, the sine of 25 is going to be h upon 450, and h is going to be 450 multiplied by the sine of 25. All right, now you've got your h multiplied by 9.81 and multiplied by g. Option D is your correct answer. Yep, that's the answer. Then three identical springs L, M, and N are connected as shown. Spring N has a load attached to its lower end. Extension of L is X. extension of L is X, okay, and they're identical. That means extension of M is also gonna be X, but extension of N is gonna be different. Why is it gonna be different? Because if you look at the force, this entire force is acting on this first spring F, but on these two springs, it's half the force that's acting, okay? So this means that there is double the force acting on spring number N as compared to L, which is F upon 2. If this is F, if this is double, then you know that force is proportional to extension. If force has become doubled, then will the extension also double? Yes, definitely. So now the extension of this N is also going to be 2x. Which row of the table gives extension of these springs? The extension of N is going to be x. Extension of M is, sorry, it's not x, it's 2x. It's 2x, okay? We just calculated that, it's 2x. And the other two are going to be equal, it's option D. Yep, that's the answer. Then 11. Okay, we are done with MCQs now. Section B. Honey is used, stored in jars at room temperature. Under certain conditions, small crystals form in the honey and move around to form larger crystals. The following extract was taken from a honey producer website. Honey crystallization is more rapid, around 10 to 15 degrees. At temperatures below 10 degrees, the crystallization is slowed down. Low temperature change the viscosity as well. Explain how the low temperature affect the movement of the slow crystals in the honey. All right, this is a theoretical question. So come on, what do you think should be the answer? Okay, so at lower temperature, the viscosity
Can you
will
show the worksheet
rise.
again?
Yes, just a second. The viscosity will rise at lower temperature because at lower temperature, you've got the more drag force. And if more drag force, then that means the viscosity is going to be higher, okay? Greater at lower temperatures, and so the crystals will move more slowly. This increases the viscous drag force and the crystals would move more slowly, okay? These are 3 points. Crystals move. Question 12. All right, this is also related to viscosity. A small ball bearing is released at the top of a measuring cylinder oil as shown. This is your ball bearing released at this oil. So this is that same experiment which we did in paper 3. Okay, the cylinder and the oil filled and then the ball is being thrown downwards. The sphere falls, reaches the maximum velocity. This is going to be your terminal velocity. Okay, calculate the maximum drag force acting on the ball bearing. If the radius is given and the viscosity are given, just calculate the drag force. So use the Stokes law, 6 pi eta multiplied by r multiplied by v. Eta is your viscosity, r is the radius, and v is the velocity, terminal velocity. And just plug in everything and you get your answer. Okay. Now add to the diagram below to show the flow of the oil during the ball bearing as it falls uh, through the measuring cylinder. All right, what would happen over here? Okay, so this is very important. As these lines move forward, as soon as they reach or they approach the ball bearing, they'll move this way. Okay, this is how the flow will change. Clear? Let's look at it. Two outer lines continuously straight or slightly uninterrupted. Okay, pass the bearing two inner lines curved around the ball parallel to one another, and both lines at least length of one diameter beyond the ball award the marking point. Okay, turbulent flow is included. Do not give the mark. Okay, this is not turbulent. This is laminar flow. So yeah, we got the marks over here. Then 13. Trumpets are commonly made from brass and alloy of copper and zinc. The main tube of the trumpet may be produced by pulling the brass tubing to reduce its diameter and then bending its shape. Okay, so the brass tubing might be pulled or it might be entered, whatever they told us. Explain how the property of the brass enables it to be pulled to reduce the diameter of the tubing. Right, so they asked you to for the reduction in diameter for the first part and the why it can be bent into shape in the second part. So bending is due to the malleability because it changes shape.
Wait, sir, you're lagging.
Okay, right. So it changes shape under compressive force, and I would suggest that you learn this. Okay, that with malleability,
Yeah.
it's the compressive forces which are accompanied, and with ductility, it's the tensile forces which are accompanied. Okay, this is ductile because it changes shape or undergoes permanent deformation, undergoes plastic deformation under tensile forces. And over here it's compressive forces. That's the key difference in between them. Whenever the diameter is being reduced, that means you're drawing it into thinner uh, form of that object. This is usually used for thinner wires, but you can draw it into thinner pipes, thinner tubes, whatever you want. And over here, in the second part, why is the shape of the tubing changing? Well, the shape is changing because of the malleability. Okay, malleability, when you apply compressive forces on it and changes shape without reduction in the diameter, rather this actually increases the diameter. Okay, that decreases the diameter. So this completes this question actually. Now moving on to question 14. Student carried out an experiment to measure the extension of a rubber band. She determined that the extension of rubber band as applied forces are increased. She plotted a graph of the results. Okay, these are the graphs of the, this is the graph of the results. Determine the work done in stretching the rubber band. All right, this is the working part. The work done in stretching this rubber band. Total work done. This is 5.5, and this is raised to the power of -2. Right, you need to calculate the area under this graph entirely. All right, so basically the idea over here is you need to break it into smaller segments. For instance, you break this into a first triangle, then this is your trapezium type of thing, and then you got your this third trapezium. Okay, let this be a1, this be a2, this is be a3, and calculate the areas of each one of them independently and get the work done in stretching this rubber band. Okay, this is going to take you some time. Okay, although it's just area calculation, but they've given us 3 marks for it. Why? Because there's a lot of working for it. So I'm not doing this, of course. You have to do this yourself. You know how to calculate the area for trapezium, right?
Yeah.
Half
Half into
times
times A plus B in
to
brackets
height
into
into sum of
height.
parallel sides. Yeah, the height into sum of parallel sides. If this is A and this is B, then A plus B. All right. So for this one as well, but make sure that you take the correct A and B, okay? And of course, the marking scheme will give a range of answers for this because this is not gonna be an accurate answer. See, a range is given from 0.46 to 0.48, right? Try to be as close as possible, or try counting the number of boxes. If you think some part is missing out, each box will represent a certain area. If you look at the box dimensions over here, these are the 10 boxes are representing 1, then 1 box is representing 0.1, and if 10 boxes are representing 5, then 1 box is going to represent, okay, 20 are representing 10, then that means 1, 2 would be representing um, 1. Okay, if 2 would be representing 1, then 1 would be representing 0.5. So 0.5 against 0.1 would be the area of the smaller box. You can count the number of boxes as well under the graph, but that's going to be more time consuming. It's better to calculate the areas directly. Okay. Then sketch on the axis above a possible graph for the unloading of the rubber band. All right, so remember one thing for the rubber band does not undergo plastic deformation, okay? Rubber band remains elastic. So when you unload it, a typical graph which is gonna go back. The extension will try reaching back, and this extension will return back to 0. Okay, because it does not undergo plastic deformation. This is the unloading graph. It's gonna be below the actual loading graph. Okay, this is the unloading graph. Is this clear?
Yep.
Okay, that for only for a rubber band. Okay, not for a wire, not for a spring. only for rubber band. Wires and springs do undergo plastic deformation. Right, now this is done. 15. The graph shows how the displacement of the racing car along a straight track varies with time. This is a displacement, this is a time. Okay, displacement time graph. If you look at the graph, it's not a straight line, it's a the gradient is changing gradually. This means the velocity is changing. Velocity is not constant. If the velocity is changing, that means acceleration is also present. Now, student use a graph to calculate the velocity of the car at 15 meters, if to 15 seconds, and he used this formula. Oh, 300 divided by 15, which is 20 meters per second. Meaning at 15, he just found the displacement, he found the time, and then he just used the formula speed is equals to distance upon time. Can he use this formula over here? In presence of acceleration, can this formula be used? This is the S is equals to VT formula, right?
Yeah.
So can this be used in presence of acceleration? When is this formula
No.
used? This is,
When there's no acceleration.
yeah, this is used when acceleration is 0. So this means this for student got an incorrect value and calculate the correct value. So for the correct, state why this is incorrect, because acceleration is non-zero. Acceleration is non-zero and velocity is changing. So the formula cannot be applied. Now to calculate the correct value, you have to use the equations of motion. Okay, they told us, okay, we just need to, okay, you actually don't need to calculate the equation of motion at this time. All you need to do is just find out, draw a tangent at this point, and calculate the gradient of that tangent. This will give you the velocity, okay? Well, of course, you'll have your ruler, you'll have to draw a more better line than this one. I've drawn it freehandedly, okay? And this tangent has to pass through this point. And then you have to calculate the velocity at that particular time. Okay, why did I not use the equation of motion over here? Well, the reason for that is because they didn't tell us in the question that acceleration was constant. Okay, they didn't tell us that acceleration is constant. Okay, this is not told anywhere in the question. So this means that the car might be going at a constant acceleration or it might not be going at a constant acceleration. Okay, so and equations of motions can only be applied when the car is moving at constant acceleration. Okay, so that's why, since they didn't mention it, it's better to draw a tangent over here and calculate the gradient of that tangent. Okay, I'm not doing the gradient stuff, you can do that yourself. Okay, and please do these questions once you get done with the class. Okay, I'm leaving them for your practice. Now, the gradient of the graph continued to increase as the car traveled along the track. After 20 seconds, the rate of increase of the gradient began to decrease. Explain why the rate of increase of the gradient decreased. All right, what is the rate of increase of the gradient? Rate of increase of the gradient. First of all, the gradient is change in displacement upon time, which is actually your velocity, right? Rate of increase of velocity means change in velocity upon time. Change in velocity upon time means acceleration is what they're talking about. Okay, rate of increase of the gradient means rate of increase of the velocity, and rate of increase of velocity means acceleration. So now what's happening to the acceleration? They told us that the gradient of the graph continued to increase. After 20 seconds, the rate of increase of the gradient, meaning the acceleration, it started decreasing. Okay, so this means acceleration is non-constant. Okay, it's not constant. Acceleration started decreasing, they told us. Now explain why the acceleration is decreasing, why the rate of increase of gradient it decreases as time passes. All right, so why will the acceleration decrease? Well, acceleration depends upon the force, right? Net force. Net force is ma. If the net force decreases, then that means acceleration will have to decrease. And why will the net force decrease? Well, this is a car, right? A racing car, and it is moving along a straight track. So of course, it's they didn't tell us that this car has gone around a corner or it has moved around a corner. It didn't apply brakes anywhere. Then why is its acceleration decreasing? The simple explanation for this is that the forward force which was acting, this forward force caused the velocity to rise. And as the velocity rises, will the resistive forces also increase? Definitely, air resistance will increase as the velocity increases. And the air resistance, a time will come when it will balance out the force, right? And when the air resistance balances out the force, then the acceleration is going to become zero. So the logical answer for this is that as time passes, the velocity increases, the air resistance increases. And if the air resistance increases, the net force, it decreases. And the net force decreases, that means the acceleration decreases, which is actually the rate of increase of the gradient, right? So as time passes, velocity rises, air resistance also increase.
Sir, are you writing it down?
Sorry?
Okay.
Yeah, I'm writing it down. Can't you see? Can you see it? Is this visible?
Okay.
Yeah, all right. Air
Video was
resist.
stuck at the other question.
Oh, is it still stuck?
No.
All right. Air resistance is increasing, and if air resistance is increasing, then that actually means the net force decreases. Net force decreases, acceleration also falls, and acceleration is the rate of increase, okay, of the gradient. Clear? Did you get this?
Yeah.
Acceleration is decreasing, drag force is increasing, or the resistive force is increasing. Okay, just 2 points we mentioned everything. We got the marks. Yeah, all right. Now moving on to 16. Swain carried out an experiment to investigate the motion of an object undergoing constant acceleration. Okay, acceleration has to stay constant. That actually means we can apply equations of motion on it. The student uses a linear air track to provide frictionless surface for a glider of mass m. Okay, this is a glider. It can move freely on uh, this this place, which the track, the air track. Okay, this is air track. That means the frictional force has become how much? It has become zero. Okay, air track means it's gonna stay above this track, so friction is zero because it's due to the air inside the track. Now, and they told us in the question that the frictionless surface is there. A mass m is attached to the glider using a light, inextensible thread placed over the frictionless pulley. This is the frictionless pulley. This is the inextensible thread over here. The air pump is switched on and the glider is released. Okay, air pump is switched on means the glider means the surface has become frictionless. Okay, the air makes the surface frictionless. And now this is released. As soon as it is released, it will pass the first light gate. As soon as it passes the first light gate, the stopwatch will start. And that's gonna be your time zero. And as soon as it reaches the other light gate, the stopwatch will stop and it will record the time. Explain how the glider moves with constant acceleration. Okay, how will it move it with constant acceleration? Well, the frictionless pulleys, the track is frictionless. Track is frictionless. The mass is constant. This means the forward force is constant. The forward force is constant and there is no resistive force. This means that the net force is your forward force, right? It is your mg. And since the net force is constant, we know from Newton's second law that force is proportional to acceleration. Force is constant. This is constant. That means acceleration will also going to be constant. Let's look at the marking scheme. Weight creates a force on the glider. We did mention that. We did mention the mg. Tension in the string is constant, or the resultant force is constant. We did mention that as well. According to Newton's second law, there is a constant acceleration. All right. We got all the 3 points. Did you get this question?
Yeah.
All right. Should I write down the answer?
Yeah.
All
Oh no,
right.
I can just see the marking scheme.
Okay, but you know how to phrase it, right? You don't need to exactly copy these points. You need to like word them as well. Or it's up to you. Yeah, the points will actually gain you the marks. One light gate is placed at the release position of the glider and the second one is placed further along the track. Both are connected to a computer and the time taken for the glider to travel between the two gates is recorded. The manufacturer of the light gate states that the light gate system has a precision of 10 meters per second. What is meant by precision? Precision actually means the least count. Okay. It means the smallest value of time that could be measured by the light gates. Okay, you could just copy that down or write it from the marking scheme. The smallest division, smallest reading on the scale, smallest change in input. Okay, that's the first one is better. The smallest reading or the least count that can be read or measured. Okay, least count that can be, least reading that can be measured. And the smaller the precision, the better it is. Okay, for a better precision, it has to be smaller, meaning you should be able to measure very small values with the same apparatus. So if I were to compare micrometer screw gauge with a vernier caliper, the micrometer screw gauge will have a better precision because it can measure, it has a smaller least count. Okay. Then part 2 says the student is to use the equation S is equals to ut plus half et squared, where u is 0, and the graphical method to determine the acceleration. Describe the procedure the student would use to determine the acceleration. Okay, this is a unit 3 question. Okay, the half and a are the constants. So if they are the constants, so can I say that s is proportional to t squared?
Yeah.
So that means I have to draw a graph of s against t squared. It has to be a straight line passing through the origin. And the gradient of that line, what will that represent? What will that gradient represent? Look at the equation.
Half A.
Perfect. It's going to represent half a. And then the acceleration can be calculated just multiplying the gradient by 2. Okay. So how can the student use, how can this procedure be used to determine the acceleration? So the graphical portion has been covered. This would be approximately for 3 marks. What about the remaining 2 marks out of the 5? Well, for the remaining 2 marks, you have to describe the experimental technique that he has to use. Okay, first of all, this glider should be released just next to the light gate. Okay. So as soon as he releases the glider from here with the particular mass m, okay, he can use various values of masses. He can use various different masses, right? To get different, well, why is he using different masses? Wait, we need different displacements and we need different time and squared. So that means the light gate's distance can be varied, right? The distance between the light gates is the s. Is this the displacement? Displacement is s, right? This is the entire answer, okay? S is equals to ut plus half at squared, where u is 0. So this is what we get. S is equals to half at squared. Half a is constant, meaning half a is going to be the gradient of s against t squared graph. This is the graph that we will plot. To get the acceleration, we need to multiply 2 by the gradient. He can determine or measure the distance using a meter rule and the time using the light gates. The distance can be varied by changing the position of the light gates. Okay, or the time taken by the light gates can be varied using that method. Clear? All right, so the photograph shows a cyclist performing a jump. To reproduce the photograph, the camera shutter is opened at regular time intervals. Okay, so different photographs have been caught at different times. Okay, so this is actually a projectile, a sort of a motion. Now, with reference to the photograph, describe the motion of the cyclist as he performs the jump. All right, so the motion needs to be described. So what happens initially? Well, as the cyclist comes over here, he had a certain velocity. Then as he jumps, what happens to the velocity? It falls, right? The vertical component of velocity actually falls. Horizontal will stay constant. Actually, wait, this is a cyclist, so of course the horizontal will not stay constant because air resistance will be there. And then as this cyclist moves or passes the maximum position, and as he goes down, the velocity increases, but then in the negative direction. And as the velocity increases in the negative direction, as the cyclist falls down, the velocity reaches the maximum position or maximum value as just before hitting the ground. Okay, so these are a few points. Let me write them down as well. That this is a key term over here, that the time interval is regular. Okay, so first of all, um, as this cyclist jumps, you could also mention that the cyclist is undergoing projectile motion. Okay, the vertical component of velocity is changing, horizontal component of velocity is constant. Vertical component of velocity, it decreases first and then increases. Okay, the distance in between each image is constant, the horizontal distance in between them, because there are 4 marks for them. So you have to describe both the velocity as well as the displacement or the distance. These are the two things you need to describe in this image. Okay, horizontal distance between each adjacent image is constant, and the vertical height also taken from the image increases and decreases. Increases first and then decreases. These are the points you need to include in your answer. Okay. Okay, so now the path of the cyclist is shown. The cyclist takes off with a velocity of 9.8 meters per second. So the takeoff velocity is 9.5 meters per second. At an angle of 10 degrees to the horizontal, the total time taken for the jump is 1.8 seconds. Meaning from here all the way till here, the time is, this height is needed. All right. To calculate this height, you have the total time, right? Okay, before you have the total time, let me tell you something. The horizontal component of velocity is going to stay constant throughout the motion, or throughout the motion, the horizontal component of velocity is going to stay constant. And using the horizontal component of velocity, we can calculate this distance, but we won't be able to calculate that distance. Okay, we don't need to go into that method then. All right, to calculate the height, we can use, we'll need to use two displacements or two distance. That is the total height, and then we need to subtract this height from it. Okay, now the total height, how to calculate the total height and how to calculate this height. Okay, first of all, you'll need to calculate the vertical and horizontal, just the vertical component of this velocity. This is 9.5 meters per second, and this is 10 degrees. So what's going to be the vertical component? It's going to be 9.5 sine of 10, right? So vertical velocity is, can you calculate a value for this, please? I want to solve this question entirely. Sine of 10, which is?
Sine of 10 is 0.17.
Into 9.5. You did that, right?
Oh, no. 1.65.
4.65?
1.65.
All right, 1.65. We have the vertical velocity now. You need to calculate this height. Let me call this height h1. Okay, basically the height, this one, the height it took, the height till which the ball reached, or this cyclist actually reached the maximum height from this top of the hill, from this dotted line. This height needs to be calculated. Well, you have the initial velocity, which is 1.65. You know that the final velocity is going to be 0. You know that this height needs to be calculated, and you know the acceleration is 9.81. You have the final and initial velocity, and the acceleration and height needs to be calculated. You don't have the time, so you don't need the time. You can use the formula v squared equals u squared plus 2as. The final velocity is 0. The initial velocity is 1.65. The acceleration is going to be negative of 9.81 because as you go up, your acceleration is going to become negative. So now calculate a value for this h1. H1 is going to be 1.65 divided by 2 into 9.81. Can you please get me a value for this, please? H1 is going to be 1.65 divided by 2 into 9.81.
0.084.
Okay, 0.084.
Yeah.
Right, meters. This is your H1. Now, once you have the height it takes for this ball to go up, meaning the maximum height from this mean position. Now it's time to calculate the total height. Total, meaning the total vertical height. Let me call that H2. To calculate the total vertical height, you'll need to know the time it took this ball to fall over here. All right. You know that the initial velocity of the ball at this particular point is going to be 0 because it's at the vertical position, at the maximum position. So the vertical component of velocity is going to become 0. Now you have the vertical component of velocity. You need the h. You know that the acceleration is 9.81. You don't have the time and you don't have the final velocity. But they did give us a total time. If they gave us a total time, that means we can calculate the time it took for this this cyclist to reach from the maximum to the 0 point. But this time is not for the second half of the journey, but rather it's for the total journey. So for that, what we can do is we can calculate the time it took for the cyclist to reach the maximum height from the hill, meaning the first part of the journey. Okay. How can we calculate the time? Well, we can apply any formula we want. Time t1 to reach max height from the hill. Apply ut plus half at squared, or apply any formula you want because everything is given to you. Okay. So time, well, I'll use v is equals to u plus at. Yeah, v is equals to u plus at. Where t is needed, so t is equals to v minus u upon a is equals to time. Now the final velocity is 0, but the initial velocity is 1.65. So difference between 1.65 and 0 is 1.65 and the acceleration is 9.81. So what's the answer to this? 1.65 divided by 9.81. 0.168 seconds.
Yeah, 0.168.
Okay, now we got the time of the first half of the journey. We have the total time as well. Can we calculate the time of the remaining journey? Just subtract them, right? It's gonna be 1.8 minus time t2, 0.168. So 1.8 minus this answer is gonna be 1.63 seconds. So it took 1.63 seconds to fall to the earth from the max position. So now we have the time. We have everything that we want. All we need to do is just find out the displacement. So S is equals to ut plus half at squared can be applied. U is going to be 0 because from the maximum height when the ball falls, its initial velocity is going to be 0. So half times A is 9.81 and the time is 1.63 squared. This will give you the displacement h2, meaning the height h2, this one. .03 meters. Now you've got the total height and you've got the max, the height from the hill. You've got h1 and h2. The difference in between them is going to be the height of the hill. Okay, so the height h is equals to 13.03 minus 0.84, 0.084, 12.9. 13 meters, 12.9 meters, same thing. 13 meters. We got our answer. Clear? For the horizontal distance, we'll need to consider the horizontal component of velocity, which can be calculated using the formula v cos of theta, right? Velocity is 9.5, so it's going to be 9.5 cos of 10. You know that the total time is given to you. It's 1.8 seconds. So to calculate the horizontal distance or displacement is going to be horizontal component of velocity multiplied by the total time. So it's going to be 1.8 multiplied by 9.5 times cos of 10. So it'll give you the horizontal distance jumped. Okay. Yep, that's the answer. That's how they calculated it. C says, explain briefly why the cyclist briefly has a feeling of weightlessness during this jump. Explain why. Why do we get weightlessness? Well, weightlessness always occurs when the acceleration becomes equal to 9.81 or when the person is in free fall motion. Okay. Fw is equal to, if you remember the weightlessness formula, as we fall down or as we go up, what's the formula for weightlessness? Weightlessness force is equals to, or the apparent weight is equals to mg minus ma or mg plus ma, right? These are the two formulas that we have. Whereas this is the
When
formula when we
doing
are
the
going,
MG plus MA?
when ascending. And this
Okay.
is the formula when descending. Please remember this. This is important. We have done it a lot of time, but this is important, okay? Now, when this acceleration becomes equal to 9.81, the cyclist will get a feeling of weightlessness, okay? But in reality, the acceleration does not remain 9.81 throughout the motion, because in reality, air resistance will be there, right? Over here, we've just assumed that air resistance is not there, but in reality, this cyclist will be facing some air resistance, due to which the acceleration will be less than 9.81. Now, time will come during a certain time when the acceleration was 9.81, which is most probably the initial time, just just after the cyclist jumped. That would be the time when the cyclist would feel weightlessness, because the acceleration at that time is going to be 9.81. Okay. And why does he feel weightless? Because acceleration has become 9.81 and he has entered free fall motion. And anything that is falling freely will undergo weightlessness. There is no normal contact reaction force acting on him from the bike. The cyclist is falling with the same acceleration as the bike, or the acceleration of the bike is 9.81. Falling freely. Okay, they actually gave both the points in one mark. So we have, there is no normal contact force acting
What
upwards on him.
what topic does weightlessness come under?
What topic does weightlessness come under? Remember forces, Newton's forces, equilibrium. Okay, but mark, which actually we gave 2 points, but both of them were the same thing. So the second mark is given for this point. So please learn this point, that there is no contact in between. There is no normal contact force, or there is no contact force or no normal force acting on this person from the bike. That's why there is no contact force from the bike. So the person would be falling or would
So wait,
feel
what is FW called?
apparent weight.
Okay.
The mg is your weight, the actual weight, and ma, the a is actually the acceleration with which the person is moving, either up or down. Okay. In this case down, and in that case up. Clear? Is this question clear? Should I move on to 18?
Yeah.
Physics investigates the behavior of materials used in packaging. A sample of plastic ribbon is supported so that it hangs vertically. A mass of 960 grams is used to apply a vertical load, and then a sample of plastic ribbon extends. Okay, so you've got some ribbon, and then there's some load applied. Its initial length was L, and then after this load was applied, its length increased, okay, and it extended by a certain extension. Calculate the strain produced in the sample of the plastic ribbon due to the load. where the young modulus is given to you, the width of the plastic ribbon is given to you, and the thickness of the plastic ribbon it's also given to you. The width and the thickness are given to you. That means, can you calculate the cross-sectional area, right? If this is a ribbon, then most probably its cross-sectional area is gonna be somewhat rectangular, right? So to calculate the
Right.
area, just multiply these two quantities which are given to you. 1 into 10 raised to the power minus 2 multiplied by 1 raised to the power of minus 4. You'll get your cross-sectional area this way. Okay. You have the formula for young modulus. What's the formula of young modulus?
E is equals to stress over strain.
And what's the other formula? FL over
FL over AE.
AE, where E represents extension. Okay. Now they want us to
Extension.
calculate the strain. Want us to calculate, where did that go? Yeah, strain produced. Strain is extension upon length. Over here we have length upon extension. That actually means if we take this length upon extension to the other side, it's going to be young modulus multiplied by extension upon length into f of 1a. This is your strain, so they want us to calculate the strain. Okay, keep the strain at its place. A strain is equals to the force upon the young modulus into the cross-sectional area. You got the cross-sectional area using this formula. Okay, so it's going to be 10 raised to the power of minus 6. Multiply that by the young modulus given to you, which is 2.5 raised to the power of 9. And the force of the load, the mass of the load is 960 grams. It has to be converted to kgs. So it's going to be 960 into 10 raised to the power of minus 3. This is kg. Now this is the mass. This is not the force. For the force, multiplied by 9.81 as well. Get me an answer to this, please.
But I cannot see the screen. Why did we have to rearrange it? Like, why not just substitute it into the original formula and then get it?
Yeah, you can do that. You can do that as well. But you'll have to then calculate the stress first. You'll have to calculate the stress first then. Stress is force upon area. Now you need to have the force in the area, do that, calculate the stress and then put it here. Then rearrange this. So the strain is gonna be stress divided by the young modulus. The stress is actually this force upon area. So you could just plug it in here. It's also gonna give you the same thing which we got it from there. Okay. When a plastic ribbon is pulled over a sharp edge and then released, the ribbon becomes permanently curled as shown over here. This is a plastic curve. Okay, it becomes curled. Physicists investigating this effect carried out a series of experiments using the equipment shown over here. This is your load and this is your sharp edge and then the ribbon and then the rotating cylinder. A rotating cylinder pulls the ribbon over the sharp edge. A tension is created in the ribbon by attaching the load to the free end. Okay, as the ribbon is pulled over the sharp edge, the tension in the upper surface is greater than the tension in its lower surface. When the tension is removed, the ribbon curls. So just why the difference in the two tensions causes the ribbon to become permanently curled. So the surface which has a greater tension would extend more and may undergo plastic deformation, due to which the outer, okay, the outer, they mean this one. This one, the upper surface means this one, okay? This surface has more tension as compared to the inner one. Then that means the outer surface would undergo more deformation. Okay, this outer surface, which is there, there are two surfaces, the outer, the upper one, and the lower, the downward one. The outer one will undergo plastic deformation, and it will, if it undergoes plastic deformation and it undergoes more extension than the inner one, then that means it would bend. And if it bends, then that definitely means it will undergo curling. Okay. These are the 3 points you need to include in your answer. Should I write it down or is it okay? Should I write it down?
Yeah.
All right. Just a second. Okay. The outer surface or the upper surface has more extension. So according to Hooke's law, will extend more. more as compared to the inner surface. Okay, it will undergo plastic deformation. The surface which was extended more, there's a high chance that it will undergo plastic deformation. Since it is extended more, since the outer surface it will bend to produce curling. Okay, that's the answer. The
Wait,
physicist,
can you scroll back to the answer?
sorry? Now the physicists repeated their investigation to by pulling the ribbon with different tensions over a round edge and over a sharp edge. They had a round edge and a sharp edge. The graph shows how the diameter of the curl varied with the tension for each edge. Okay, so the diameter of the curl and the tension. So the greater the tension, the lesser would be the diameter of the curl. Okay, for the round edge, this has a flatter gradient, and for the sharp edge, the gradient is more steeper. Okay, so now let's see. State how the diameter of the curl varies with the tension for a given edge. It varies inversely, right? Inversely because of the shape of the graph. This is a typical hyperbolic curve for inverse relationship. 2 says, state how the diameter of the curl is affected by the shape of the edge for a given tension. Okay, for a given tension, for instance, this is a tension. Okay, T. Diameter for the round edge is going to be more than the diameter of the curl sharp edge. This is a sharp, this is the round. So the round one is more as compared to the sharp edge. Reducing the speed of the rotating cylinder decreases the diameter of the curl. Explain why. Alright, so now you are reducing the speed of the rotating cylinder. This would decrease the diameter of the curl, and explain why. And yeah, that's the last part. Okay, let's look at the rotating cylinder now. This is a rotating cylinder. If it rotates faster, the diameter of the curl is going to be more. And if it rotates slower, then the diameter of the curl is going to be lesser. So reducing the speed means force is applied for a greater time. On the wire, and if force is applied for a greater time on the wire, that means there is more time interval or more distance or more length in between adjacent curls. There would be more length in between adjacent curls. Therefore, diameter would decrease. These are the only 2 points you required for this answer, because this was a 2-mark answer. And we didn't check out these answers, right? Greater the tension, the smaller the diameter. So inversely related. The idea that greater the area of the blade, the greater the diameter. The sharper the edge, the smaller the diameter. Okay. Is more than that. So this is the idea which we gave over here. Okay, the diameter of the sharper the edge, the smaller the diameter. We did mention this idea in this answer over here as well. Now coming to the last question, 19. Water-propelled jetpack enables a flyer to be lifted up into the air. Water is pumped up through the pipe to the pack and then ejected at high speed downwards from a nozzle at the base of the jetpack. This is more like a rocket. If you remember, in rocket there are gases which are moving down. In rocket there are gases moving down which are applying upward force on the person. Over here the weight, the water is going down in the water. As force is applied on the water, equal and opposite force would be applied on the person by the water. We can say that this is actually Newton's third law pairs. Force 1 and force 2 are going to be equal and opposite. These are going to be Newton's third law pair forces. I explained with reference to Newton's laws of motion how the ejection of the water from the base of the jetpack lifts a flyer into the air. Okay, so first of all, force will be applied on the water by the jetpack, right? Then what would happen?
And then the
According
water
to
would exert an
equal and opposite force, but according to which
equivalent
force?
force back on the jetpack.
Yeah, and according to which law?
According
Newton's third law.
to
According to
third
Newton's
law.
law, water will apply an equal and opposite force. And they ask us to explain in terms of Newton's laws of motion, not just one law, but more than one laws. So what is force? According to Newton's second law, force is rate of change of momentum, right? So there is change in momentum of the water. So the change in momentum of the water per unit time also causes a change in momentum of the person. Okay? There is rate of change of momentum of the water. Is the force. Rate of change of momentum of the water per unit time. No need to mention this term over here. Rate of change of water or rate of change of momentum of the water is the force applied on this person. Okay, because they asked us to give in terms of Newton's laws, not just one law. There's a downward force on the ejected water. Due to Newton's third law, it exerts equal and opposite. There's a resultant force on the flyer jetpack. This is Newton's second law. Accelerates upwards according to Newton's first law, second law. Okay, these two laws we didn't mention. There's a net force. Okay, we did mention this force, the net force one, because this rate of change of momentum, this is equals to the net force. This is Newton's second law, due to which the person would accelerate. Okay, so you can mention it over here. Okay, force is applied on the water in the downward direction. Then, according to Newton's third law, equal and opposite force applied on the person. And according to Newton's second law, there's a net force on the person. Then according to the same Newton's second law, due to the net force, there is going to be some acceleration on that particular person. Okay, we got the 4 points. Moving on to the next question. Part B says, right, this is a forces question. The flyer, the jetpack, and the water contained in the jetpack at any instant can be considered to be a system. The diagram shows the forces acting on the system. Right, tension in the pipe, the weight, the force from the ejected water. All right, this is one force, this is the second force, this is the third force. Show that the maximum weight it can be lifted is 700 Newton. If the tension in the pipe is 310 Newton and the force of the ejected water is 960 Newton. All right, we need to show that this weight is 700 Newton. We need to show this value. We just need to calculate the value of the weight. All right, to calculate the value of the weight, if you look at it carefully, the weight is balanced by this upward force. Okay, how many upward forces are there? If you look at it carefully, there is an upward force due to this ejected water, and there is an upward force due to the tension in the pipe. But the upward force due to tension in the pipe is not actually acting upwards, but it's acting downwards. Right? Due to this tension, there is a force downwards in the direction of the weight. What is this force? The component of the force that's acting in this direction due to the tension in the pipe. What's going to be its value? Will it be 310 cos of 40 or sine of 40? This orange arrow.
This is going to cost.
Yep, cos of 40. The 310 cos of 40 and the weight are acting downwards. And what is this component? This is 960 cos or sine 12.
Oh, which one?
This one, this arrow, the blue one. If this force is 960, what's the blue one? If this is 960 Newton and this is the angle 12 degrees, then what is this? 960 times cos of 12 or sine of 12 degrees?
Sine.
Cos of 12. Look at this. It's a triangle like this. This is 960. This is 12. And it's a side adjacent to the angle. So it's going to be cos of 12. Okay.
Oh, okay.
Yeah. Now forces are upwards and downwards. You just add them and equate them and you'll get your answer. The 310 plus the weight is going to equal the 960 cos of 12. 310 cos of 40 plus the weight is 960 cos of 12. Can you calculate this answer, please? So the weight is going to be 960 cos of 12 minus 310 cos of 40. It's going to be 701 Newton, which is 700 Newton approximately to one significant figure. And that's the answer that they wanted us to show. Clear? Is this clear? All right, part 2 says, as the flower initially rises from the surface of the water, the tension in the pipe can be considered to be negligible. So initially means when the time was 0. So at that time, the tension in the wire was negligible. Then the pipe was negligible.
Repeat the start.
Sorry?
Can you repeat the steps again?
Which one? These?
For the
As a flyer initially rises from the surface of the water, the tension in the pipe can be considered to be negligible. Initially, when the time was 0, the tension was 0. Then calculate the minimum initial vertical acceleration of the flyer system. Assume that the weight of the flyer system is the value calculated in B part 1. Okay, so weight is 701.54 Newton. This is your weight. They're asking us to calculate the minimum initial vertical acceleration of the system if the tension is 0. Okay, to calculate the vertical acceleration, what do we need? The vertical net force, right? And the vertical net force is going to be upward forces and downward forces and their difference, right? Now, in this question, there's one thing that we need to take care of, and that is the tension in the pipe is 0. We need to consider this fact. If the pipe is 0, then that means this component will also become 0, right? If this component is 0, then that actually means the weight itself is being balanced only by the 960 cos of 12, and it's not actually being balanced, but rather the 960 cos of 12 is acting upwards and the weight, the 701, is acting downwards, right? Can we calculate the net force or the resultant from these two values? This is going to be your resultant. Which is 237.47 Newton. Now you have your resultant force. You can apply the formula F is equals to ma to calculate the acceleration. Acceleration is equals to resultant force 237.47 divided by the mass of the system. What is the mass of the system? The mass of the system is actually the weight of the system divided by the 9.81. Weight is 701. Divided by 9.81 means that the numerator will get multiplied by 9.81. And now you'll get your extension. This is 3.3 meters per second squared. Yep, that's the answer. 3.3. Is this part clear? Now the rate means the mass is given to you. And the density is also given to you. Mass and density can be used to calculate the volume, right? And then once you have the volume and you have the cross-sectional area, you can get the speed. Okay, and now listen very, very carefully. 49 kgs per second means that in 1 second time, there is a mass of 49 kgs in there that is passing through the nozzle. In this question, they are asking us to show that the velocity of water is 10 meters per second as it leaves the nozzle. They told us that in 1 second, 49 kg of water is moving out of the nozzle. And they gave us a density of water. We can use it to calculate the volume of the water that is flowing out in 1 second. Volume is equals to, well, cross-sectional area multiplied by the, volume is equal to density upon the, well, density is equals to mass upon volume. So volume is equals to mass upon density. So the mass is 49 kg and the density is 1030. This will give you the volume. This 0.0457 meter cube. And once you have the volume, you can use it to calculate the length. Now listen very carefully. Pipe looks like a cylinder. In a cylinder, you've got the volume, the total volume. The length of the cylinder is L. Cross-sectional area is given to you. It's 4.6 raised to the power of minus 3. You can multiply these two to get the volume as well. 4.6 raised to the power of minus 3 when it is multiplied by the length will give you the volume. Now, the volume which we calculated is 0.0475, which is equals to 4.6 raised to the power of minus 3 multiplied by the length. So the length is equals to 0.0475 divided by 4.6 raised to the power of minus 3. And so the length turns out to be how much? 4.6 raised to the power of minus 3. And that's 10.3 meters. This is the length which is covered in 1 second. So this is actually your speed, 10.3 meters per second. Get it? 10 meters
Yeah.
per second. This is 10.3 is 10. You understood it? The flyer stays at constant height of 12 meters above the surface of the sea. It can be assumed that the water enters the jet pack at the same speed as it leaves the nozzle. Calculate the minimum power of the pump that is used by the system. Told us that the height is 12 meters above the surface of the sea. And it can be assumed that water enters the jet pack at the same speed it leaves the nozzle. Okay. Flyer, where is the flyer? Here it is. Sorry. Here he is. He stays at a speed of, at a height of 12 meters, as it told us in the question. And the speed with which the water is being ejected over here, this speed, this is given to us, which is, we calculated that speed actually. It's 10.3 meters per second. It's the speed with which the water is being ejected. The height is given to us, which is 12 meters. And now the power is needed. Okay. Think of it this way. You've got, and it's for 4 marks, so this means there might be more than one step involved. Okay. So now the height is constant. That means the flyer is at a constant, the flyer has some potential energy, gravitational potential energy. And the speed of water is also there, it's 10.3 meters per second. And the mass of water during that second is also given to us in the start of the question, which is 49 kgs per second. 49 kgs per second. Using this data, we can calculate the kinetic energy. Using this data, we can calculate the potential energy. And when we add them, we will get the total energy. And since this is per second and this is also per second, wait, that's obviously going to be per second, but this is per second, this energy will also going to be for per second. And that will be your power. Okay, so let's do that. Did you understand what I just said? Find the kinetic energy of the water and the potential energy of the person.
Okay.
Calculate the potential energy of the person. The height is given, but the mass, where will you get the mass from? Well, it's in the previous part of the question, where you had the weight of the person,
From the JE.
701 Newton, right? So use the MGH. The weight is 701 point something multiplied by the height, which is 12. Okay, mg is actually your weight, right? 701 into 12 is 8412. Calculate the kinetic energy, half mv squared, half times mass, which is mass is going to be 7.1701 divided by 9.81 multiplied by the velocity of the water, which is moving out, is 10.3 squared. This will give you the kinetic energy. (3790 joules). Now, this is the energy of the water that is ejected, and that's the potential energy of the person in the air. So the minimum work which is done is 8412 plus the 3790. Okay, so when you add them up, you'll get your answer. Let's verify it. Potential energy plus kinetic energy. What is the answer that we get for this 8412? 12,000, 1202. What did they give? And divided it by the time. What is the time? Half times mass times v squared. We did this, and mgh 49 kgs per second. Oh, wait. This mass that we have over here, this is not the mass of the person, but rather this is the mass of the water that is ejected. Okay, because the pump is doing work on the water, not on the person. It's doing work on the water. First it is throwing water up, and then that water, as it goes up, is coming down. Okay, water goes up and then returns down.
Okay.
So the pump is 49 times 9.81 times the height, which is 12. So this is not going to be 8412, but rather it's going to be 5768.28. Add the 37902 5768. 49 into 9.81 into 12 plus half times m times this is v squared. They didn't square it in the marking scheme. I think this is a misprint, but this should be squared. Okay, the potential energy plus the kinetic energy of the water which is ejected. Okay, they want us the work done by the pump. Okay, the pump. The flyer stays at a constant height. It is the pump, the rate at which water leaves a jetpack, and it is the pump which is doing the work on the water. So the calculate the minimum power of the pump that is used by the system. So the minimum power is actually the power, the work which is done on the water. So it's first the water is raised to a height and then it's given some energy. That energy is converted into, in addition to that, it's given half mv squared. So this is a minimum energy which is required. Okay, so mgh plus half mv squared, where m is the mass of the water, not the mass of the person. Okay, this gives you 8400 watts. And this completes the paper. Yep, that completes the paper. Finally, did you get this?